Hello ladies and gentlemen, my name is Prudek and I also work at Turris, and my position is the guarantor of the data collection team, the team behind Sentinel development. I would like to thank my colleague for the first part of the presentation and will now continue with the second part. I will focus on data processing inside our server infrastructure, the Sentinel pipelines. I will start with a short story. Once upon a time, in a small country in the heart of Europe, a new internet research project was born. Its main objective was to monitor network traffic of an average Czech household and protect it against potential threats. The project was well designed for few research devices, but then, as luck would have it, the once research-only device became so popular that almost everyone did want to own one. New generation of the device was released and was named Turris Omnia. But as the number of the device grew higher, the once well-designed project started to have problems with managing the enormous flow of data. You just saw the most recent numbers, so we clearly had to redesign everything, and I will now tell you how we succeeded. The first step was to get rid of single central database and replace it with stream data processing. We decided to split the whole architecture into several pipelines, separate pipeline for each data source. For example, one pipeline is for minipods that were already mentioned. Each pipeline consists of few boxes. Each box is then a small piece of code that modifies, enhances, splits, or filters the floating data in several ways. Some of the boxes even perform a real-time analysis of the data. The boxes are interconnected using ZeroMQ messaging technology, which we've chosen after a deep research. The data itself are therefore packed and sent in small pieces, which we refer as to Sentinel Network messages. ZeroMQ was our choice from several reasons. It allows us to load balance data flow between several duplicated boxes, and the boxes doesn't even need to be on same physical machine. ZeroMQ provides us with several messaging patterns: request reply, also known as client server, publish subscribe. We use this pattern to publish updates of our dynamic firewall, and finally pipeline, also known as push-pull. We use this pattern in our pipelines to implement that already mentioned load balancing. As you probably mentioned, there's no place for any broker. The boxes are connected using ZeroMQ directly, which is the reason why its authors call it TCP on steroids. Actually, the word zero in ZeroMQ doesn't only mean that there's no broker. It should also mean zero administration, zero cost, and zero waste. However, several trade-offs must have been made to achieve this zero behavior. One of them is, as far as we know, lack of any internal heartbeat. We had to implement it on our own. Another drawback is encryption, which is possible, but requires certificates distributed over a different secure channel. Since we use ZeroMQ mainly on our own secure infrastructure, the encryption is not an issue. And to exchange ZeroMQ certificates between nodes outside our infrastructure, we usually use HTTPS as the secure channel. This is the case of dynamic firewall updates. This slide demonstrates how to set up ZeroMQ in each box in our pipelines. I use Python in this example for two reasons. It's well readable and our pipeline boxes are written in Python as well. So let's pretend we have a pipeline with several boxes. The two boxes displayed here may be located somewhere in the middle of the pipeline. Their code would be very similar. Actually, only the box addresses and ports used for communication and their actual task would differ. Let's begin with importing ZeroMQ module and creating ZeroMQ context. 0MQ context is just a space from which we take 0MQ sockets. We create one pull socket for ingress and bind it, and one push socket for egress, which we connect to the next box in the pipeline. Everything's done. Until we realize that one of the boxes is not happy anymore, and it's overloaded by the processing of incoming data. You probably know what will happen now. We will duplicate the unhappy box and will end up with two happy smiling boxes. But the developer is not smiling anymore. He would need to modify the first box's code so that it would distribute the messages equally between the two boxes that follow. The code would need to be modified also with any other configuration change. We solve this issue by implementing Sentinel Network library, which serves as a framework that handles all the network box configurations. The library is available on our GitLab pages and is released under a free license. For the library purposes, all intended 0MQ connections are supplied in form of resource via configuration. The boxes itself only define which sockets we have to supply for them to work, like basic input and output sockets. All the details about socket's direction, pattern, or destination are then shipped as a resource via command line configuration arguments. The Sentinel Network library also provides the boxes with basic exception handling and implements heartbeat monitoring across the network. Another important feature of the library is the definition of standard Sentinel Network messages. Standard Sentinel Network messages are used across all the boxes as the default data exchange unit. They consist of two parts: message type, which is hierarchically structured in a similar way like MQTT topic. Message type also determines which format we should expect from the second part of the message payload. Message payload stores the data fields itself. For example, action type and attacker's IP address in case of message originating in minipods. Sentinel library also ensures that the message payload is encoded using message pack before leaving a box. The whole message is then sent using 0MQ send multipath method. Using Sentinel Network library, the configuration of the previously mentioned boxes would be as follows. All the boxes require to supply resource only for one input and one output socket, simply named in and out. The sockets are intended to connect to the previous and following box independently of their respective duplications. We therefore supply three resources for the first box, one resource to connect to its predecessor, and because we duplicated pipeline box number 2, we have to supply both of them as a resource for the box number 1. The egress 0MQ socket of the first box would therefore connect to two remote 0MQ sockets at once and would distribute the messages equally between them. The configuration of the remaining two boxes is very similar, with one difference. We expect only one predecessor and one follower for each of them. To ease the usage of 0MQ and to remove most of the boilerplate, the Sentinel Network library even defines subclasses for three most common types of Sentinel Network boxes. The most used one, and also the one we've already met in this presentation, is Sentinel Network Pipeline box. It expects one input and one output socket definition in its resources. This code, which I'm showing here, is actually not an example, but one of our real boxes. This very box serves as a filter in our dynamic firewall pipeline. It only forwards those messages which have a valid and global attacker IP address in their payload. The rest of the messages is simply dropped. The second type of predefined boxes is Sentinel Network Generator box. It serves at the very beginning of a pipeline and usually performs decoding from other protocols to 0MQ or fetches data from other sources. It expects only one resource for its single output socket. We use this type of box, for instance, as a source of data for our dynamic firewall pipeline, where it fetches data from Honeypot as a service project. The third and last predefined box is Sentinel Network termination box. As the name suggests, it is used at the very end of our pipelines. There could be a database storage attached to it, or it could, again, translate 0MQ to a different protocol. By default, we have to supply only a resource for its ingress socket. Now, you should have a brief knowledge of all the basic patterns and techniques used inside Sentinel Pipeline, so we can delve into details as I'll show you what we built on top of it, and you can as well. It all begins at a Turris router. We already know Minipod component. Besides it, there are a few other components. Firewall logs collector collects attempts to scan device open ports. Both Minipod and Firewall logs collector then forward the data reports to router Sentinel interface, the proxy. Proxy knows Sentinel server address and sends message packed data using MQTT to our infrastructure. There, Mosquito broker receives it and forwards to data processing pipelines. That's where all the fun begins. Each data processing pipeline starts with Smash. Smash is subscribed to pipeline-specific MQTT topic, Minipod in this case, and translates MQTT to 0MQ. The payload is basically left untouched, and the topic is transformed to Sentinel Network standard message type. After that, well-known Sentinel pipeline boxes follow. Basic payload inspection is carried out by sanity check, and the message is forwarded to Unpacker. Unpacker extracts Minipod type from payload and inserts it into message type. Then, the message is enriched by country code and autonomous system number based on GeoIP database record of the attacker IP address. This pipeline ends with termination box called dumper, which stores the preprocessed records to our database. The database then serves as a source of data to our front-end component, Sentinel View. Using Sentinel View, you can browse countries with the most active attackers, you can view most used passwords and logins, or you can get even more detailed information about the most active attackers' IP addresses. But this is just the beginning, while we are working on improving Sentinel View capabilities right now. Now let's get back to the pipelines. We've studied Minipod pipeline, and maybe you noticed that there was no big need for stream data processing when we stored the result to a database anyway. So let's move to another pipeline, Sentinel Dynamic Firewall. Sentinel Firewall arms the Turris routers with real-time adaptive firewall and is the most important Sentinel data analysis. The data used for its computation are collected from the same devices they protect afterwards. The theory behind the dynamic firewall is as follows. Each router is able to report malicious behavior of a remote IP address. These reports are based on Minipod or Firewall logs collector observations. Each router is able to assign each IP address a score based on the severity of its actions. The score bonus of each router is limited, and the authenticity of the reports is cryptographically verified. When an address accumulates score high enough, it is placed on a list of dangerous IP addresses. The list and its updates are published back to all routers immediately. If we do not register any further report, an IP address is removed from the list after a defined period, currently 1 day. Now, let's check how this corresponds with our pipelines. The data for the dynamic firewall pipeline are preprocessed in one of the data processing pipelines, Minipod in this example. Component T in Minipod pipeline works in a similar way like Unix T. It splits the data flow to several ways. Then, our already familiar component, called filter, comes and secures that only valid and global addresses that are not present on our safe list are being processed by the dynamic firewall. The scoreboard component then uses Redis as a storage for running scores of the addresses. It also assures that no router is able to add more score than a limit defines. When the scoreboard detects that one of the addresses reaches the threshold, the address record is removed and the address is placed to the list of dangerous addresses. At the same time, a new message containing that address is issued and sent to the rules collector. Rules collector keeps a copy of the current list and forwards its updates to the dynamic firewall publisher component. The dynamic firewall publisher component is a nice example of Sentinel Network termination box. It ends the pipeline and forwards the message using encrypted 0MQ publisher socket to the routers or other Sentinel dynamic firewall clients. If an address that is already on the list does not accumulate another high score in the next period, its Redis record simply expires. Expiration of the record is notified to the event listener using Redis keyspace notifications, and the address removal is published to the Turris routers and other dynamic firewall clients the same way like before. I intentionally emphasize that also non-Turris dynamic firewall clients could be used. They could be used freely, and we even published Sentinel Dynamic Firewall example client on our GitLab pages. The Dynamic Firewall protocol uses 0MQ publish subscribe pattern and 3 types of Sentinel Network standard messages. The info list message contains complete list of dangerous IP addresses in its payload. It should be used only for the first initialization of a client application, mainly because of the transportation overhead. The info delta message delivers regular updates of the list, either additions of a new address or their removals. The info event message is not needed for dynamic firewall functionality, but it can be used to visualize how the dynamic firewall works. It contains events that led to score increase of any attacker address. Now, you should have enough knowledge to use a modified example dynamic firewall client and even to build more advanced applications. For example, the following one. We call it the WizUp. It is going to become integral part of Sentinel View. WizUp connects to Sentinel Dynamic Firewall Publisher interface and visualizes the current list of dangerous IP addresses, its updates, and also the events originating in Telnet, SMTP, FTP or HTTP minipods. Occasionally, you can see events originating even external sources. For example, HAAS, which means Honeypot as a Service. Honeypot as a Service is an external source of dynamic firewall data. We call it external, although HAAS proxies are present on Turris routers because the proxies do not send the data to Sentinel infrastructure directly. Instead, all the honeypot traffic is routed to full-fledged honeypots operated by CZNIC in Prague. All the collected data are fetched to the Sentinel Dynamic Firewall Pipeline by the Sentinel HAAS client box. The last thing we had to solve was the cryptographical signing of reports sent by Turris routers to our infrastructure over MQTT. We could not sign each report by the internal crypto chip directly, because the chip is wear down by the process. Instead, we use the crypto chip only to obtain unique certificate that is subsequently used in MQTT communication. To automate the process, we created an automated certification authority called Certificator. At first, certificate component on the router issues an HTTP request to Certification API. The Certification API checks whether the certificate is already present in its Redis cache. If so, it is successfully returned. If there is no certificate in Redis, certgen is asked to authenticate. A random nonce is sent to certgen and certgen signs it using the crypto chip. The response is sent back to Certification API and handed to Certification Authority using Redis queues. The Certification Authority checks authenticity of the signature. This is possible thanks to the fact that we have public parts of the keys used in routers' crypto chips. If the signature is valid, Certification authority checks whether certificate for this router was already issued, and if not, creates a new one. The certificate is then sent back to the router and is used in the MQTT communication with the Sentinel infrastructure. Now you should have a brief knowledge of all the pipelines, and so this is the end of the presentation. We both would like to thank you for your attention and would like to ask you for your questions. You can contact us also using the following email addresses or visit our documentation or GitLab pages.